Okay, good afternoon. So I'm going to present one of the examples that have been developed by TCB2, and specifically Loretta before presented the whole set of examples. We decided to present this one that basically, if you wish, is the easiest one, the simplest one of the in the category of retaining walls. This is because we can see that also the simplest case may be informative on some issues, and also in terms of comparison with the previous Eurocode, previous version of Eurocode 7. So the one that I'm going to present is the first one, the gravity wall on sand sloping backfill. Apparently a very simple example, but I will show you that there are always some hidden part, in simple cases. This is the old example. You see that basically it was just a retaining wall with a sloping backfill of 30 degrees, and the idea that the backfill could be, the groundwater in the backfill could arrive to this level because of the presence of this hip wall, hole, and the characterization was taught in terms of a set of SPT tests, and then from this there was the derived value of characteristic value of the angle of friction, and from this characteristic value then the design value were computed. But basically there are two issues. One is that within the TG we decided that it was better to start directly from the characteristic value. This is because a lot of work has been done in the new version of Eurocode 7 to work on the characteristic values. We have seen this morning also the guidelines that we can follow to arrive to the, say, characteristic, nominal, and representative values. So in order to avoid to get confusion into the people, we decided we are going to start with the representative value. And once we decided that the representative value was 30 degrees, then there was one issue with the original example, that is that considering the material factor approach, we typically reduce the value of the representative value, and we arrive to a design value that is less than the slope of the backfill. And therefore a problem arises because in that condition the backfill is not anymore stable. Indeed, also the formulation that are reported for the evaluation of the active air pressure in the new version of Eurocode 7 exclude the possibility of evaluating the active pressure in such condition. For this reason, we decided to slightly change the example, reducing the slope to 20 degrees. And for this reason, there is not a possible direct comparison with the previous example, but I'm going to show you the peculiar point in which we can have a comparison with the points in which we can have a comparison with the old example. And also we considered that typically a good practice is to design the drainage system in such a way that the backfill is not, we do not have the water table in the backfill, especially also because it's a permeable backfill in this case. So we decided to retain the case with the groundwater in the backfill, but to consider this as an accidental action, considering two different design situations. One design situation that is the, say, normal condition of the wall, in which we have a dry backfill, and therefore this situation is associated basically with permanent loads. We have to apply the factor of safety that we apply to the loads in a usual condition. But the second design situation is associated to a malfunctioning of the drainage system. In this case, water level can rise in the backfill, but this has to be considered like an accidental action, and therefore we have to take all the safety factor on action equal to 1. So basically this is the summary of the assumption on the parameters. I'm not going to comment on this because it's rather standard and we do not have a lot of time. So the first design situation, dry backfill, inclination of 20 degrees is a medium dense silty sand, and we assumed a representative value of 30 degrees for the calculation. Second design situation is the one with the water, groundwater in the backfill, and obviously the idea of having two design situations means that at the very end you are going to take the worst case for the design of your wall. So basically, in addition to the assumption that were done for the first design situation, we have the assumption on the water behind. So first step is the evaluation of the geotechnical complexity class and the selection of consequence class, and considering that is, say, this is a rather standard wall, we end up with a geotechnical category that is GC2, so we do not have neither to amplify the factor of safety on the action, neither to amplify the factor of safety on the materials. So all of these are basically equal to 1, and we can proceed in the evaluation of the action and the resistance of our wall. The active earth pressure was evaluated according to prescription of Eurocode 7 part 3, and specifically with the formulas reported in clause 7. Formula 7.3 is the one that was recalled before by Sebastian, and figure D2 that allow us to evaluate the coefficient of active pressure in this condition. Also, the bearing resistance was calculated according to Eurocode 7 part 3. As Sebastian was said, this is covered by clause 5, so basically it is the classical formula that is reported in 5.5, and sliding resistance the same from the same clause of Eurocode 7 part 3. Toppling verification was verified according to the prescription of part 1 and also of Eurocode 0. One aspect is important, and I will be back on this, that in reality toppling is not a failure mode that we expect in this condition, but for completeness of the example we had also reported the calculation. So now if we go into the calculation, first step is to select the approach that we want to follow for the calculation itself, and according to what is reported in table 7.2, that is basically very similar to table 5.2. 7.2 is for gravity retaining system, 5.2 is for the, say, shallow foundation, but obviously both apply, both are coincident in this case. We have the possibility to proceed either with the material factor approach or with resistance factor approach. These are detailed here in terms of combination between the factors that we apply on action and on materials or resistances. So basically we have these 5 possible combinations. In particular, the first two, 1A and 1B, are to be used together, meaning that we have to repeat the calculation with both combinations and take the worst condition, and in alternative we can use one of the other 3. So as I said before, in design situation 1 is say ordinary condition for the wall. We have to apply these partial factors. In design condition 2 is an accidental action. We apply partial factors equal to 1. The partial factors were extracted from the table A.1.8 of Eurocode 0, and these are reported over here. Basically are different considering the combination that we have seen before, but I will be back on this in one moment. The same way table 4.7 in Eurocode 7 part 1 reports the partial factors that we apply to material properties, and we have seen before in table 5.2 the partial factor on resistances. Obviously, we are not applying all of these together, but we are applying this consistently with the different combination that I described before. And so if we follow this approach in this very simple example, here is the reason to have a simple example, because we then can condensate everything in say a single slide. If we apply the design combination number 1, we said we have to repeat in 2 different conditions, 1A, 1B, traducing what is, using what is written in the table before, we get that we have a factor on actions that is, on the effect of actions, that is 1.35, and on the other side a factor that is applied on materials equal to 1. And this is absolutely the same that what we would have get with the old or the current Eurocode 7 with the design approach 1, combination 1. Similarly, in the second case, we have that if we apply, we get 1 on permanent loads and 1.5 on friction angle. That is the combination 2 or DR1 in the present Eurocode. 2C is, I would say, something like a new approach, because it's not similar to...
It's the old DA3.
Yeah.
Okay, sorry.
Is okay, so...
Say,
No, this is my mistake. It's okay.
No,
Because from what I tried to trace it back, I found something different. So here we are missing DA3. Okay, and then we have the last 2 combinations that basically in this simple case coincide with the old DA2. These are the actions that are applied on the wall. Obviously, this is the complete set of action. The earth pressure and the pressure from the water in the backfill, and the pressure on the bottom of the wall. And whenever we go to then apply this for sliding, bearing capacity, and toppling, then we have to consider which weights are, which actions are favorable and unfavorable, always remembering that the action from that the components of the same action have to be treated homogeneously. So this is for sliding. This is for bearing capacity, where we can have the doubt that the weight of the wall to be favorable or unfavorable. So if this is the doubt, we have to run twice the calculation and take the worst condition. And this is for toppling. As I said before, toppling in reality, is a real problem only when we have a rigid base, but for completeness of calculation, it is evaluated also here, because the calculation would be the same for a rigid base. And these are the final results in form of a table. For the design situation 1, so where we have a dry backfill, as we said before, we have a double calculation on the bearing capacity, because we can have that the wall self-weight can be favorable or unfavorable. This is not the case, obviously, for sliding. So, repeating the calculation, we have these 2 conditions. Basically, what we get is that the bearing capacity is ruled by the case in which the wall self-weight is favorable. And these are the final results. We said that there is, as I said before, this was the old DA1, this was the old DA2, and this is the old DA3. Sorry, we are missing also here that indication. And what we get is basically that there is quite a substantial difference in the dimension that we get for the dry case. This is something that has to be covered, obviously, in the National Annex. And the material factor approach with the combination 2C is the one that is providing the largest dimension of the wall. When we go to the design situation number 2, we have that basically in this second design situation things a bit collapse, because obviously we do not have we do not differentiate as a function of the safety factor on actions, because they become all equal to 1. So basically we have only 2 possible dimensions for the wall, and these are both larger than the one that we got in the dry case. But basically again we say that in the material factor approach we have dimensions of the wall that are rather larger than the one that we get in the resistance factor approach. So to summarize some lessons learned, even by a very simple case like this, we can say first of all that the bearing capacity for this design example, but this is something that is happen quite often, is the driving ultimate limit states for the design. The design situation 2, that is the one associated to malfunctioning of the drainage system, is the one that at the end drives the design. So this means that confirms the great attention that we have to pose to groundwater, and especially to be sure that the drainage system is always functioning in a perfect way, I would say. Material factor approach leads to a substantial increment in the design of the base if compared to resistance factor approach. And specifically combination 2C is the one that would lead to the most conservative design for the dry backfill. So if we exclude the case of accidental action, that would lead to a substantially larger dimension for the base. In my opinion, this basically means that we need to pose a lot of attention on national determined parameters in the national annexes, because it is important then to have a specific choice on the path that we can follow between material factor approach and resistance factor approach to avoid ambiguities. So with that I finished. So thank you very much for your attention.